Welcome everyone to another live session for the online course. Some of you are live, some of you sent questions by email, and we're ready to roll.
Okay, the first question is from somebody who is on live from Julian. Have you heard any details of the HDST, which is the proposed successor to the JWST, which I should point out has not even been launched yet?
Right, so astronomers have to work ahead, and the demise of Hubble is not yet upon us. Hubble's still doing great work, and astronomers are preparing for JWST launch date 2018, probably October. It's not locked in absolute concrete yet, but pretty close. 6.5 meter, more infrared optimized than Hubble telescope, 1 million kilometers away. So very ambitious project compared to Hubble, quite a small telescope. But both of these facilities have a particular issue that limits them from all types of survey science, which is they have very small fields of view. That's almost inevitable with modern telescopes with moderate f ratios of f5 to f8. So the fields of, and with detectors the size they are at the moment. So the successor to Hubble and the successor to JWST is a survey telescope, a space survey telescope designed to do what Hubble does and what JWST will do, but over huge swaths of sky and also with extreme sensitivity. And it is enabling certain kinds of science, for example, the study of dark energy or its properties by inference at cosmological distances, and dark matter at a level of detail that just can't be done by Hubble Space Telescope, for example. So this is a concept, and it came out in the 2020 time frame, so it's going to be the next decadal survey that astronomers conduct to set their priorities of big spending of facilities for the next decade. It may not even go in the decade of the 2020s, but hopefully it will. So that's the way astronomers have to work ahead. They deal with decadal surveys that concatenate all different interests and special groups of wavelengths of astronomers into one priority list for that upcoming decade. So this survey telescope in space is probably going to emerge as the highest priority for the subsequent decade.
So Elmer, who is on live with us, would just like to know, what is space?
What is space? That's a great question. I don't think we've ever had it in 35 hours of online Q&As over the last year or so. Excellent question. It's a bit of a mystery. What is space? The simple answer that doesn't really directly address the question is that space is defined in terms of our gravity theory. Space is not really the absence of something or anything. In modern general relativity, space is actually a physical and mathematical construct, and it's of course a hyphenated construct called space-time. So in general relativity, the best and current theory of gravity, now 100 years old and still going strong, space-time is a combined entity with 3 coordinates of spatial direction and 1 coordinate of time dimension. And the linkage between these two is significant because it implies that space and time are coupled in a fundamental way. I'm still not answering exactly what space is, but I'm adding an important layer to the thinking about space to recognize that it's correlated or linked in the theory with time itself. That is to say, there can be space situations which alter time, and there can be time-like situations that alter space. So in general relativity, space appears as what is called a manifold. A manifold is a purely mathematical term. If you look up manifold in a mathematical dictionary, it's essentially a geometric concept that involves multidimensional apparatuses in number theory, basically, so they're independent of any physical reality. And space in general relativity is indeed a mathematical entity. It's the space-time manifold in the theory. So one answer, maybe even a profound answer to the question of what space is, that it's a mathematical construct, because we explain its properties in the presence of matter and energy in terms of a highly mathematical theory. And that describes both the space and the time that flows in that space. So I still haven't totally described what space is, but given you a slightly different sense. And the other thing that needs to be said, of course, is that space is a commodity that is not finite. It's not finite in terms of the universe that we occupy, where we have visible space that's accessible to us through our telescopes in the history of time since the Big Bang, but that does not need to be all space. So it's potentially infinite commodity. And it's also a fungible commodity because in the accelerating universe that we live in, driven by dark energy, and even before we knew about that, we knew it was expanding, the space is expanding too. So more space-time is being created continuously as the universe evolves. So whatever space is, it's obviously not valued in the same way that a commodity would be valued, because we can essentially have as much of it as we want and as much of it more as we want.
Okay, so the next question is sort of related. Kendall asks through email, is there any research that proves or shows that the universe is infinite, or is there some sort of container that holds it all within its limits?
Right, it's a reasonable question about the nature of space, its finiteness or infiniteness. So astronomers there's a sort of observational and a theoretical answer to that question. The observational answer is that astronomers have not, through their observations, detected any limit to space. So for an observer, an observational cosmologist, space could be infinite, which is to say that we see out to a certain distance. That distance with the largest and best telescopes is about 46 billion light years in any direction. So that's a visible, accessible to telescope universe that's 92 billion light years across. And that's the totality of space available to us through direct observation. But since space is expanding, and actually at an accelerating rate, it's essentially certain that there's space beyond the limit of our visible telescopes. And so the theory has to be appealed to in terms of what that limit might be. And the theory actually is not very indicative, because if our universe emerged as a space-time fluctuation from a quantum construct of multiple space-time fluctuations, then the underlying space-time, or the space-time that we sample are part of in an expanding universe, could be infinite. And so the theory absolutely accommodates an infinite universe. And observation does not say otherwise. So at the moment, that's the best way to think about it. The space could indeed be infinite, and the theory accommodates that notion.
All right, so we have several people who are wondering about the age of the universe and the size of the universe. So let's start with James, who asks, how can we see stars that are 13.7 billion years old? Wasn't the universe much smaller back then?
We don't actually see stars that are quite that old. The age of the universe is an important number because we can determine it two different ways. We can determine it through the model, the expanding universe model. We can measure the current expansion rate and how it's changed over time to predict, to calculate through the model an age of the universe. We can also measure the age of the universe by the age of the oldest things in it, where our age measurement of those oldest things has to be based on some physics, not Big Bang physics, but actual stellar astrophysics. And we do both things. So the Big Bang model, the expanding universe model, gives an age of 13.8 billion years. The measurement of the age of the oldest things in the universe, which hopefully does not exceed that number, since the universe can't be younger than the oldest things it contains, is a more difficult procedure. The oldest stars we reliably measured the ages for are about 13 billion years. So that's going back roughly 94% of the age of the universe. It becomes much harder to find stars before that time. It's even harder to measure the age of galaxies, which are assemblages of stars. And so at the moment, we haven't seen the very first generation of stars that we believe lit up the universe when it was quite young. We expect, and JWST was built in part to answer this question, that earliest epoch of light in the universe, or the oldest stars, or the oldest stars and the oldest galaxies that we can find, will have ages of about 13.3 to 13.4 billion years. In other words, it took a couple of 100 million years for the universe to go from a hot, dense, smooth state to one lumpy enough to form stars and galaxies. But that's a supposition. So the straight answer to the question is that the oldest things we see and measure their ages of are about 13 billion years. But we're speculating that there will be yet older objects to find. But recognizing how early in the universe they are, they're going to be very faint and very distant. And to the last part of the question about that the universe was hotter and denser then, absolutely true. So at the age of the oldest objects in the universe was roughly 10 times smaller than it is now, which means it was 1,000 times denser and also 10 times hotter. And so it was a quite different place, but it was still a place where stars and galaxies could exist. They tended to be, the galaxies that existed then would have been smaller galaxies, dwarf galaxies, ferociously forming stars. And the stars that formed would, of course, have been a little different from stars in the nearby universe because there were very few heavy elements then. They were made by the first generation of stars. So the first stars that formed were almost purely hydrogen and helium.
Okay, and then to kind of round it out, we have I think we'll take one more question about the age of the universe because there's lots of people who are interested in that today. And then we can move on with some other topics. But Metin asks, how can we calculate the age of the universe as 13.7 billion years, which is sort of addressed, but maybe you could address more directly. But then they have a question about time passing for a cosmic microwave background radiation photon because of general relativity. Hasn't time passed more slowly? Is the universe seem less old to it because it's been traveling through the universe at the speed of light?
So two interesting questions. I'll deal with them separately. So to get into a little more detail about how we measure the age of the universe through the model, through the expanding universe, the Big Bang model. The simplest way to think about this, which is how we thought about it 30 or 40 years ago, is that with telescopes, starting with the Hubble Space Telescope, one of the things it was built for, we measure the present expansion of the universe, the expansion rate of nearby galaxies relative to the Milky Way. And that was a key project for the Hubble Space Telescope, and that's called the Hubble constant. The expansion rate of the local universe in units of kilometers per second per megaparsec was a key project, and the number is about 70, high 60s, or 70 kilometers per second per megaparsec, which means if you go a megaparsec away, 3.25 million light years, a typical galaxy is moving at 70 kilometers per second away from us. If you go twice as far away, the velocity is twice as high, and so on. In simple universe that's expanding uniformly over time, if you take the Hubble constant and invert it, it has the units of time. And so 1 over the Hubble constant, the current day expansion rate, is a rough estimate of the age of the universe. It's essentially extrapolating a constant expansion rate back to a time when everything had 0 separation. So that's mathematically very simple to do. And so 1 over the Hubble constant is a first order estimate of the age of the universe. But that number is an overestimate of the age of the universe because it does not accommodate the fact that the universe for most of its history was decelerating due to dark matter and normal matter. And so you can see, if you think about it graphically, that if you project back a constant expansion rate, but the expansion rate was faster in the distant past, then you will overestimate the age of the universe. So to properly estimate the age of the universe from the expanding universe model, you have to know how much dark energy and dark matter is in there, because the dark matter for most of the early history was slowing the expansion down over time. And more recently, the dark energy has been speeding it up again. So basically, in the model, you plug in your best estimates for dark matter and dark energy, and then you get a revised estimate of the age of the universe. And that's what leads now to it was 3.7, it's been adjusted to closer to 3.8 billion years. So that's a pretty good estimate in the model of the age of the universe. It's actually accurate given the way we measure dark energy and dark matter to a few percent. The second question about whether the photons in the microwave background experience any relativistic effects as they travel through space is a very interesting question. Because as the questioner probably realizes, in general relativity, we have a situation of gravitational redshift, where photons that are traveling through a gravitational field are redshifted. They have their energy degraded because they're traveling through intense gravity. That is a strong effect, and it has been measured. But of course, now we're talking about a situation of the entire universe. And so the entire universe does have gravity, but the gravity locally is fairly weak. So photons in the microwave background do not experience a general relativity gravitational redshift per se. They are in fact in a reference frame of the entire expanding universe. So to shortly answer the question, no, there is no special effect. There's no tired light effect or gravitational redshift that applies to the photons in the microwave background as they move through an expanding universe. But as the universe expands, the underlying space-time is expanding, which means the metric, the distance between any two space-time points, increases. And so the wavelength of radiation is now increasing because it's referenced to an expanding space-time. And that's what causes the radiation to be redshifted as it travels through the universe. And so after 13.7 billion years of expansion, those photons from the microwave background that were red photons or dull red photons at the edge of the visible spectrum when the universe was 1,000 times smaller than it is now, they've been redshifted by that same factor of 1,000 to become microwaves, which is how we measure them with present-day telescopes.
All right, Chris, so Guillermo from the live chat has a question. There are some techniques to search for extrasolar system planets. What technologies are available to find planets like Planet 9, and are they similar to the exoplanet techniques?
It's a good question because the solar system is now hot again as we look in the outer solar system and are hypothesizing the existence of a very large planet hitherto undiscovered. And so the short answer is no. These techniques are for looking in the outer solar system for large objects are really very different from the exoplanet method. The exoplanet, almost all the exoplanets have been found by two methods. Basically, the approach is to look at stars, nearby stars. Most exoplanets have been found around stars that are within a few hundred or a few thousand light years, which is a small fraction of the size of the galaxy. So we look at those stars, and we either look for a periodic dimming of that star caused by a planet crossing the face of the star, or we look for a periodic Doppler shift of that star caused by the tugging of the exoplanet as it orbits the star. So in looking for exoplanets, we just target nearby stars, nearby sun-like stars usually, but doesn't have to be. Now people are looking at dwarfs quite a lot because there are a lot of dwarfs. And you look for indirect evidence of the exoplanet. So you're targeting stars, they're known stars, and you have two very precise, well-understood methods for finding an exoplanet should it exist. The only thing that would cause you to miss the exoplanet are if the orientation of the orbit was transverse to the line of sight. Obviously, the eclipses are only possible when the planet will just happen to cross the face of the star, so the alignment has to be pretty good. With the Doppler method, the alignment doesn't have to be quite so tight. But if the planet is orbiting in the plane of the sky around the star, then there's no net Doppler shift, so we wouldn't detect it. But most of these planets are detectable. Meanwhile, in the solar system, we have a quite different issue. We have an issue where any potential large solar system object beyond the orbit of Neptune and Uranus could be in a very large range of distances, not just distances out from the sun, along the ecliptic or the main plane of the solar system, but also away from the ecliptic, because outer solar system objects are often gravitationally perturbed, and so that takes them away from the uniform sheet or the thin plane of most of the orbits of the solar system. So if you think about that now in a survey, you're having to look through not just a narrow strip of sky, the ecliptic, but a broad swath of sky, maybe tens of degrees across, and you're having to look at very distant objects. They're by definition, they're beyond Neptune, Uranus, they're tens of billions of miles away, perhaps hundreds of billions of miles away, and they're going to be not very big objects with no illuminating light source. So they're just dark rocks in very deep space, and they're very faint. So these surveys have taken a long time, and they're still underway. And in fact, nailing down Planet 9 could take months, it may take even a year or so. Because knowing that it's there and identifying it as a very faint, very distant object moving very slowly from one night or 1 week to the next on the sky is quite a challenge. So the people doing these surveys, which is also the Kuiper Belt, that's how the Kuiper Belt was found and characterized, have essentially embarked on decade-long surveys with mostly arrays of small telescopes, big enough to go deep, but small enough with a fast enough focal length to do a large swath of sky with sensitive CCDs. Very difficult, painstaking work that only a few research groups are doing.
Thank you. And our next question comes from Ahmed, who's watching live. He asks, What are the complications of landing on Mars?
So I'll take this as both a unmanned and then a manned mission. So for the unmanned missions, NASA's gone through different stages with this. The first landers, which were the Viking missions back in the 1970s, were landers that stabilized with gyroscopes and had retros and just soft landed with their rockets pointing downward. And then NASA's always been able to do that. But there was a phase of time with the first of the rovers in the mid-1990s for about a decade, where NASA, wanting to protect its very valuable hardware and realizing that the Martian terrain can be quite uncertain and you don't always know exactly where you're going to land something. There's no pinpoint landing with any of these technologies. NASA opted for a safe approach, which was the sort of bouncing back approach, and that was done with Spirit and Opportunity, the two rovers, one of which is still working on the Martian surface, and with their precursor, which is called the Sojourner rover. And that's a safe technology where the payload is wrapped in a cocoon of inflatable balloons that completely surround it and buffer it, and so it bounces to a halt on the surface. Then the balloons deflate, it rights itself, and it travels off to do its journey. NASA upped the degree of difficulty for unmanned landings with Curiosity rover 2 years ago, and it will do the same again in 6 or 7 years when the Curiosity's twin goes to Mars. They used a sky crane concept, which is very challenging because it means the rover is deployed from a stabilized platform that essentially hovers above the surface and then lowers the lander down on extendable guy ropes until it senses the surface, then releases those guy wires and then flies off. That's a highly precise and very dangerous maneuver. There's many things that can go wrong. And so NASA upped the degree of difficulty, and they did so because the Curiosity rover was much more massive than the smaller earlier rovers, and they essentially thought the bouncing back idea would not work. So they had to go to a different technology. Well, with that success, of course, NASA has been emboldened to try that again. So that will probably be the way we land future payloads. For humans, the issues are similar, but the stakes are even higher, of course, because there are lives on the line. And the problem with landing on Mars is that while the gravity is low and the atmosphere is thin, the atmosphere is significant. So it's actually easier to land on the moon, where there's essentially no atmosphere, and the calculation of heating rates of a spacecraft and its buffeting by winds. Remember, Mars has quite active winds and dust storms and so on. This is a huge complication to sending a manned mission down, stabilizing the spacecraft as it lands, because it's going to be going pretty fast with no aerobraking from the atmosphere. And so you're going to have to be using retro rockets to soft land it. And it's quite likely that this will be done in a way that Apollo was done, where there will be an automated landing sequence with the possibility for human override at any time. And the astronauts who land on Mars will be highly trained and probably test pilots in the ability to take over the spacecraft to save their own lives if it came to that, but to ensure a proper outcome. And the other reason, of course, is that because the targeting cannot be super precise, say less than a football field, the possibility that you end up in a little boulder-strewn area where you put a leg of the lander on a rock and it tips over. I mean, these are real concerns that NASA's always had. That's a present danger, of course, of any of these landing missions. And so at some point for the astronauts, you'll just want human control to avoid that, which was, again, the same thing that happened on Apollo.
All right, so Kendall writes in via email something along the same lines. What do you think will be the consequences of colonies on other planets, for example, Mars? But what do you think the implications of such an accomplishment would be, good or bad?
I think the colonization of any body other than the Earth would be a spectacular event in human history, because it would obviously be the first time that, more than just for an adventure or a short-term visit for scientific purposes or tourism even, we left our planet. So the idea of a set of people who were going to live, die, and perhaps have children and subsequent generations on another world is as dramatic as the first time we left Africa 50,000 years ago. So if it does happen, it's an incredible thing. And we might also understand that such a colony would quite rapidly diverge from the human tree. Now, that's not to say they're going to become a new species very quickly, but it may only take dozens or a few hundred generations for them to literally diverge from us in the way they look, in the way their physiology works, and genetically to be close to becoming a new species. So this is dramatic stuff. When might it happen, and could it happen? Yes, there are no showstoppers to it. It's extremely expensive to set up a colony on the moon or Mars. Cheaper on the moon, of course. It's much closer. But it's an extremely expensive proposition, and it's just not clear that anyone has the money, and not even these private billionaires that are doing space race stuff like Jeff Bezos and Elon Musk and Richard Branson. Nobody really has the deep enough pockets to set up a colony right now. How much money are we talking about? It's very hard to tell. Mars One, of course, is the outfit out of Europe, out of Denmark, I think, that is privately funded, trying to send colonists to Mars. And most people don't really believe their timelines or even their technical ability to do that. Estimates of how much it would cost to set up a viable but small colony of maybe a dozen people are $100 billion and upwards. Well, we spend $100 billion on the International Space Station, so it's not an unprecedented amount of money to spend on a single project in space, but it is an extremely high number. It's 8 or so years of NASA's budget, the whole thing. So for that reason alone, and the difficulty of doing it, as well as the danger to those first colonists, I think we're probably 2 or 3 decades away from that. But note that I didn't say I didn't think it would happen, and I do think it will happen. I just think the timescale is very uncertain. I think there's going to be enough interest in it. There's going to be enough motivation to be part of that pioneer new species, to leave the Earth, to set up your own rules, basically. You're no longer governed by the UN or national law or any of the normal human social bounds and bonds, which is an interesting thing. Could be good, could be bad. So I do think it'll happen. And if I was to put a number on it, I'd say it's going to be 30 years away.
All right, John via email asks about Lagrange positions. Can you first outline the properties and uniquenesses of these points in space? And then can you explain why NASA wants to put the James Webb telescope in one of them and why Hubble was not put in one? Right, the Lagrange points, Lagrange was a French mathematician. I think he was a contemporary of, I'm losing my reference here, but he's late 18th century. So a very brilliant mathematician. And he recognized, in considering solar system orbits, that there were gravity balance points, essentially, where in a 3-body system, which say might be the sun, the earth, and the moon, you could find a place where the sun and the moon's gravity were balanced out, and so you had a stable position. There are some of the Lagrange points are stable, some of them are unstable. There are 5 formal Lagrange points in the theory. And so NASA has been using one of the Lagrange points for several missions, and JWST will be one of these. The position is about 1 million kilometers from the Earth, so it's substantially further than the Earth-Moon distance. And the reason for putting an object in a Lagrange point is if you put it in the Lagrange point that's on the opposite side of the Earth from the sun, you can be in a sun-shielded position where you're sheltered from solar radiation. So that's one reason, and it's also a very quiet space environment. No debris, no background light, super dark. Those are the basic reasons you put telescopes there. The other reason they're favorable orbital positions is that the 2 stable ones are what they say. They're stable. Once you've placed the spacecraft there and the Earth and the Moon are doing their thing and going around the sun, nothing shifts. So the spacecraft stays stable relative to the Earth-Moon system for forever, essentially. Even the unstable Lagrange points only take a very mild rocket, just a little booster rocket, nudging you every now and then to keep you at that position. So the energy cost of being at a Lagrange point is fairly low. So these are the reasons we use the Lagrange points. They're stable or quasi-stable orbital positions far from the Earth, from interference, dark, and the problem, the downside is, as you can imagine, it's very hard to get there. These are robotic
spacecraft that cannot be serviced. JWST will have to work. There's no way astronauts can go out there to fix it if it doesn't. So the downside, and why not all missions or most missions are out there, is that not many space telescopes or space observatories are reliable enough to risk them being in a place where they can't be serviced. Remember, everything on the Hubble space station, the Hubble telescope, and everything in the International Space Station could be fixed by astronauts. Not true of facilities at the Lagrange points.
All right, the next question is from Gerald, who is on with us live, and it's about telescopes. We know that an advantage of space telescopes is that they can analyze portions of the electromagnetic spectrum that are filtered by the atmosphere, such as UV. However, we know that UV causes sunburns and so forth, so apparently it's not filtered. Can you clarify?
Right. It's correct. It's a matter of definition. It's a matter of what wavelengths you're talking about. And so I think the health scientists have a different term of definition of ultraviolet than astronomers do. So I'll probably be talking about the astronomer definition. I don't know what health science defines exactly. And on your sunscreen, you'll see on the packet talk about UVA and UVB and so on. So basically, the simple part of the story is that as the wavelength of the radiation gets shorter, and so you go towards the blue end of the spectrum, the energy is higher, the frequency is getting higher, and the energy is getting higher. It's an inverse relationship. And it's that increased energy of each of those photons that gives them their destructive power. And in the case of ultraviolet radiation in humans or other living organisms, that destructive power, of course, gives you sunburn, literally, or it can cause cellular damage, or worse still, it can cause systemic mutation inside a cell. And so melanoma is a case where the energy of the UV radiation is sufficient to cause an uncontrolled cell division, and that's a cancer, and that's the worst thing that can happen out of UV radiation to humans. So not all these UV rays do get to the Earth. The atmosphere does filter some of them out, and I'm sure you've heard that as you go to high elevations, you have to be more careful about using sunscreen because more of the UV will get through. So compared to sea level, if you go up to about 10,000 feet, I think the number is a factor of 2 more of the damaging UV rays get through at 10 or 12,000 feet as they do at sea level. So it is quite a serious problem at altitude. And around the world, cultures that live at altitude, like, say, the Tibetans or Nepalese, they tend to have a lot of melanin in their skin, and they have very dark skins and their own internal protection layers in their skins. So to astronomers, the ultraviolet regime really only starts at an even higher frequency or shorter wavelength where the radiation does not get to the Earth's surface. So luckily, the Earth's atmosphere does protect us from some fraction of those UV rays, and it's essentially the ozone in the atmosphere that's doing the heavy lifting there. But as you go below the magic numbers, about 3,000 angstroms or 300 nanometers, as you go shorter than that, then the atmosphere suddenly becomes opaque. And at that point, of course, the rays don't get through, so the atmosphere does protect us from those, just as it protects us from X-rays from space. But of course, astronomy is not possible either. So you can't do anything with those radiations unless you put a telescope in space.
Right, the next question is from Alice Amanda, who is one of our longtime participants, and who likes to play Stump the Astronomer. So, have you heard of the article about apparent detection via new telescope with concave lenses of otherwise invisible terrestrial entities?
Well, hello, Alice Amanda. And that question is just cunningly a little vague enough that I don't know what it refers to. But if it's referring to the direct detection of exoplanets telescopically, which it could be, then I can comment. That's a hard thing to do. So in the exoplanet game, essentially most of our detections, of which there have been thousands now, only a few dozen have involved direct detection. So using telescopes, concave mirrors, and direct imaging to find other worlds, planets, exoplanets, is extremely difficult to do. And we've done it just a few dozen times. But it's definitely what astronomers want to do in the future, more and better. Now that we've found thousands of exoplanets, and Kepler is going to put a number on how many are Earth-like or Earth-size, we want to go to the next stage of the game. And the next stage of the game, it's not sufficient just to say there's an exoplanet there and how big it is or how massive it is. For the next stage of the game, we want to know what the exoplanet is made of, and in particular, what kind of atmosphere it has. And it's for that that we need telescopic imaging. We need direct telescope imaging of a planet that's orbiting a distant star. And our problems are simple. The problem is that this very far away, hundreds of trillions of miles to the nearest one, light years or so. And the other problem, of course, is that the planet is typically hundreds of millions, perhaps a billion times fainter than the star, and very close to it in the sky. So super sharp imaging techniques, essentially from space, are going to be required, or using interferometers on the ground, are going to be required for us to see these distant exoplanets. Like I said, we've had a few dozen examples so far, many of those in the infrared, where the contrast of the planet with the star is better. But they tend to be far-flung planets. These are Jupiters or super Jupiters, and they tend to be far from their star, so they're nothing like Earth-like planets. For imaging to start to work on Earth-like planets around Sun-like stars, which is one of the holy grails of this kind of work, is actually going to take techniques that are mostly just being tested in the lab and very rudimentary phases on telescopes. We simply don't have the means to do that right now. So I would say it's about 5 or 10 years away before we have the instrumentation suitable to do what you're asking, what I thought you were asking anyway. But it's an exciting project.
All right, Kay, who's on with us live, asks, what differences would our planetary system have compared to the way it is now if the sun were twice the volume, everything else being the same?
Interesting question, and the hypotheticals in astronomy are always interesting. You know, what would happen if, or how would it be different if? In science method, these are called counterfactuals, and they're often interesting because in astronomy we just get to see the way things are. We don't get hypothetical universes to observe, and so we have to play that game once we observe something. Or did it have to be that way, or how would it be different if it were not that way? So to your question, if the solar system included a star that was sun-like in terms of its mass, but significantly larger, the answer is nothing. Essentially, well, actually the answer is nothing as far as planetary orbits go, but there would be substantial differences as far as the properties of those planets and whether life could exist on them. So as far as the orbits go, it all relies on mass. And so since the premise of your question was that the mass of the sun doesn't change, its size changes, the answer is the orbits would stay the same. So that's the first part of the answer. But the second part of the answer is more interesting, because if you had the same amount of stuff that the sun contains, but it was distributed into a larger star, then the radiation coming from that star would change, and it would go in the direction of having lower temperature. Just as we have very large stars like supergiants and giant stars themselves, whose surfaces are much cooler than a typical main sequence star like the sun, the same thing would happen with our hypothetical sun, somehow configured to be larger in volume. That means that the stellar radiation would be shifted quite far towards the red. And that means that the energy coming to all the interior planets would be reduced. And so the simple answer is the Earth would not be in the habitable zone anymore. The Earth would be a frozen planet. Possibly, I have to do the math to be sure, but with what you hypothesized, it's possible that Venus might become habitable, because although it's 30% closer to the sun, this hypothetical sun would be putting out less energy, or putting out its energy at a longer wavelength, and so it'll be much cooler. So these are interesting questions because, of course, in different parts of the universe, we actually observe these hypothetically different situations, and we can compare them with our situation.
All right, the next question is from, again, someone else who is on with us live, and they want to know about whether we will ever master interstellar travel.
Well, yes, because ever is a long time, but in practice, not in our lifetimes. Now, I'm being I'm being even very generous because you're probably younger than me, and I'm assuming that's not going to happen in your lifetime either, because I don't think this is going to happen within a century. Interstellar travel is not impossible in principle. There's no law of physics to prevent it. There is just the difficulty of the huge distances. Remember that for the nearest stars, few light years, 4 light years, 5 light years, we're talking about distances that are tens of trillions of miles. The furthest we've been with our spacecraft, not with humans, the furthest we've been with humans is obviously just the moon, which is 250,000 miles. The furthest we've been with spacecraft is a couple of billion miles. So we're talking about tens of thousands of times further with a manned spacecraft or human-occupied spacecraft than we've ever been, even with robotic spacecraft in the solar system. So that gives you a sense of the degree of difficulty. So the only ways to do it, well, it can be done if you want a very slow voyage, but then the question is, you need a technology we also don't have in place, and maybe we'll need that century to get that working, which is suspended animation. The ability to take a human crew into a state of suspended animation or deep freeze or whatever, such that they could survive what would be a multi-generational journey. Because at the fast, with current technologies, which is to say no fancy hypothetical matter, antimatter drives, but just maybe a fusion level nuclear power plant for a rocket, which we also don't have in practice, but there's no showstopper there, the technology we understand. The best that's going to do is get us up to a few percent of the speed of light, the best, and even that will be extremely difficult. The energy cost is very high. So really, it'll be less than 1% of the speed of light. So if you take the nearest distance to a star, you have to multiply that essentially by a couple of hundred to get how many years it would take. So you go from 4 or 5 years to 400 or 500 years. So it's 10, 15 generations. And that's basically the big problem with the whole concept of interstellar travel. So could it happen? Yes, there's no rule against it. But given the physics limitations on the kind of propulsion technology we have, and then the limitations involved with the vast distances of space, which convert into time, it's an exceptionally challenging project.
Okay, next question is from someone who is on with us live, and Robert asks, is it more than probable, or how probable is it that we on Earth have been receiving messages from outer space that we just don't know how to understand?
It's an interesting hypothesis that there has been communication and we don't know how to recognize or understand it. And actually, I like the question because to me it's one of the more likely answers to the question, are we alone or where are they? Fermi's question. I think the premise that we would receive communications that we could somehow decode, decipher, or interpret is very low. Of course, I'm not dissing Carl Sagan here, but that was the premise of his book, Contact, and the film made from that book, that we did receive communications that we somehow decoded that gave us access to new technologies we didn't yet have. The odds of that are really small. If you just think about the fact that we have species on Earth with whom that are intelligent, however you want to define that, such as orcas or elephants or even chimps, with whom we share 99% or so of our DNA, or a large fraction of our DNA, and we can communicate with them. And now you're talking about creatures of unknown shape, function, and form that probably don't even have DNA, and certainly not our kind of DNA. How are we likely to be able to communicate with them? The cultural concept that we could communicate with alien intelligence is probably frail. So I think that your question is well motivated, because I think that's likely to be the case. Now, the next question is, would we know it? Could we detect the fact that there were communications of some kind without knowing what they meant? And that's an interesting question, and SETI has thought about that question quite a lot, because SETI, the search for extraterrestrial intelligence by their radio or optical signals from far away, is essentially premised on the fact that we can understand all the natural signals of the universe, all the signatures of variable stars or quasars or light signals that fluctuate or radio signals that fluctuate, and disentangle that or separate those natural astrophysical signals from something that's artificial and not a natural process. And that's the premise of SETI. It's not clear that we can do that. So is there a clean knife which you can separate natural astrophysics from unnatural intentional communication? No, probably not, but that's certainly a way to go. And of course, that would be the outcome. The outcome might be that you found a few signals that you deduced could not be caused by any known physical process, that you infer, therefore, had intelligent intention behind them, but you couldn't figure out what that intention was, nor could you decode or parse the meaning behind those signals. I think that's a possible outcome. I'm not sure I'd say it's a likely outcome, because, of course, the more likely outcome is that intelligent civilizations are quite rare in space, and so those signals simply don't exist to be interpreted.
All right, so we're going to go ahead and do one last question, and this one is from Adrian over email, Adrian has an interest in supernovas and hypernovas. Can you explain why a supernova explosion near Earth would be bad news for life on Earth? How far away would it have to be safe? And how many of these are there estimated to be near us?
Right, so we worry about supernovae because it's a cataclysm that releases the number in physics terms is 10 to the power 57 ergs. If all that came out in a second, then that would be the similar number of watts. So it's a huge amount of energy radiating in all directions. So of course, you're not in the firing line for more than a fraction of that energy. So the math sort of works out that if a supernova, a regular supernova, by which I mean just a massive star, say 10 times the mass of the sun, that dies violently at the end of its short life, or a binary system where mass spooned onto the lower mass member pushes it over the Chandrasekhar limit and it explodes, leaving behind a compact object. In either of those cases, the supernova would have to be less than about 20 light years for there to be a serious consequence to the Earth. And the boundary is set roughly by this. The effect of the supernova on the Earth is twofold. The first pulse of radiation that the Earth receives actually comes from neutrinos. So neutrinos, which are nearly but not quite massless particles that are created copiously in the nuclear reactions of any star, including the sun, but also particularly in the death of stars, neutrinos come out as a wave, and because they interact so weakly with matter, they actually come out slightly ahead of the radiation or the light that we see the supernova glowing as. So the first thing that would happen would be a pulse of supernovas, neutrinos rather, passing through the Earth. Very high energy, and even possibly causing some cellular damage. The thing that would really get us, though, however, is the UV radiation associated with the blast wave and the high energy envelope of the supernova. That UV radiation would cause an enormous pulse in the genetic mutation rate of any surface-dwelling creature. Creatures in the ocean would be safe from this, but land mammals would suffer probably a spike of a factor of 1,000 in their mutation level, and that would really ripple down through the food chain, the food web, and cause some very serious problems. It's also likely that that blast wave would affect the ozone layer, so it's like a 1-2 punch. You're going to be damaged by the radiation itself, and then the effect of the supernova intense radiation hitting the Earth is going to disrupt the upper atmosphere, and the ozone will be, if not completely destroyed, decimated, which will let more UV in, since it protects us from the UV anyway, which will keep the mutation rates high even after the supernova has faded. So it's a high degree of exposure of the Earth to damaging radiation. Also cosmic rays, so very high energy particles are produced as a byproduct of a supernova blast wave. And those cosmic rays, of course, each one is a subatomic particle carrying an enormous, packing a real punch. And yet again, more cellular damage, more mutation. And so these are the sort of components of the bad news for the Earth if the supernova is less than 20 light years away. The 10 light years is the boundary where it starts to become possibly an extinction, a mass extinction causing event. So to answer the question, how likely is a supernova within 20 light years? And the good news is not very, because we actually know the inventory of stars within 20 light years. NASA telescopes and ground-based telescopes, we've done that inventory. So any massive star that could die as a supernova has been cataloged. We know where they are. We know how many there are. And out to 20 light years, there are a few dozen massive stars, giants and supergiants. So that's mostly good news, because that's not very many possible problems. But now the bad news comes back again, because when you ask when are they going to go off, since these are stars that could and will, in fact, will for sure die as a supernova, the question now turns into when, if they're near the end of their life. And there we become uncertain again, because astronomers can't measure the properties of any of these few dozen stars precisely enough to put them into a stellar model to churn out at the end of a computer calculation the star is going to live 2,500 more years. The estimates of lifetime of these evolved stars that will die as supernova is somewhat uncertain by tens of %. And that amounts to a pretty high degree of uncertainty as to when they're going to go off, at the level of we don't know within centuries or millennia, but it could happen. And so that's the situation we're in. We probably will get an early warning, because in the late stages of a star's evolution, as it cascades through its nuclear fuels, it becomes very unstable, and its light output varies dramatically, and its energy output. And so we would see the star sort of flickering violently on the edge of becoming a supernova and dying catastrophically, probably before it happens, maybe by years and maybe by only months. I'm not sure. Again, depends on the models. So it's an interesting situation to be in. That was a great question to end with, and thank you all for participating. We'll be doing this again in a couple of weeks, and thank you. Goodbye.